Okay, today we're going to begin talking about half-lives. We've been talking about half-lives, but we're going to talk about half-life equations. Half-life, of course, is the time it takes for half of a substance to either react or decompose. So we're going to be dealing with basically like 6 formulas, and I will give you the formulas, so you just kind of need to be able to work with them. You need to kind of know what things stand for. So you're going to see A with a little 0. It's not really a 0, it's more of an O. That's going to stand for the original amount. We could even put it as AI, the initial amount. We're going to have AR, which is the remaining amount. Also could be AF for the final, so however you want to look at it. We've been already dealing with K, so that's going to be our rate constant, and we're going to have time. We're also going to see the formula T1 half, and that is, you're not going to do anything weird with that. That's just the half-life, the time it takes for half of it to disappear. So it's going to depend on the overall order, and this is overall order. And so here's our basic rate law. Rate equals just K if it's a 0 order. Rate equals K, A to the first, and rate equals K, A squared. So these are our basic rate laws that we've been dealing with. So here's our equations, and we're just going to be plugging into those and solving. So we're going to do 4 examples. Again, this is really pretty easy, so I don't really think that you guys will have that hard of a time with it. So we're going to move on. First example, it says in a dilute solution of sodium hydroxide at 20 degrees, the decomposition of hydrogen peroxide is first order. So that's kind of important that it's telling us the order there. So sometimes it'll come out straight out and tell us the order. Sometimes it won't come out and straight out and tell us. Sometimes it will give us a rate law. So notice it doesn't have anything up here, so that's another way. So sometimes it'll tell us verbally. Sometimes it'll say here. And sometimes it will just give us our K's number, and notice it is a time to the -1, and we're talking about how K is important, and will tell us. So this problem is telling us 3 ways. I will tell you, I won't always tell you 3 ways. So we're going to be dealing with the first order equations for this one. It says if the initial amount of hydrogen peroxide is 0.02, what is the concentration after exactly 100 minutes has come by? Now it is important for you to notice that this is in minutes, and you would want to check your K and make sure that it's also in minutes, minutes to the -1, or per minute to be exact. If not, you would have to change the time to match your K. You probably don't want to change your K. So always match your time to match your K's unit. That's going to be important. So I'm going to read the information again, and we're going to plug into my chart that I've got going on here. It says, so it's got a rate constant of 1.06 times 10 to the -5 minutes per minute. So that's going to be our K. So 1.06 times 10 to the -3rd. And we'll go ahead and stick that unit on there. If the initial amount is 0.02, so that is the original amount, 0.02 molar. And we have a time, and time is 100 minutes. And we want to know what's the concentration after that. So I'm looking for the remaining amount. Now sometimes you won't be looking for half-life, so you won't need to fill that in. So let's look at our equations. If we go back and look at our equations, we would want to use first order, so you want to be in here. And so you're going to want to use the formula that would have the remaining amount and original amount. Now some of you have learned in math this and this are the same equation. Anytime you have one on top and one on bottom, when you have the ln, you can separate them by taking the top minus the bottom. Well, we're going to need to use this one because our x is actually going to be here. And so you can't solve it when you're looking for it here. So my recommendation is probably to always use it like this. I think you'll have an easier time if you would use the formula like that. So we're going to be using this equation. We don't need to bring the half-life into it. If they had asked, we would just go 0.693 divided by the K to find the half-life. It wouldn't be hard. So let's go back to that problem. Let's begin working. So we're going to have the ln of AR, which we don't know. You can either put LR, if you would prefer, you could put X, minus the ln of the original amount, which was 0.02 molar, equals. Now it's very important that you remember in the formula there's a K here. You can get a lot of problems if you leave that K out. And then it is negative in front, K, 0.06 times 10 to the negative third minutes to negative 1 times our time, and it was 100 minutes. So maybe you could see those units are going to cancel out with one another. And now we just have the algebra to go on. So now to get this over to this side, I need to add the natural log of 0.02 to both sides. And I would just do it then in the calculator just this way. I would go negative 1.06 times 10 to the negative third times 100 plus the ln of 0.02. When you get to that point, that's what the, whoa, here we go with our pen. Let me see if I can get that to undo. It does not like me to write in. There we go. The ln of x equals, and so you would get this number. Let's see if I wrote this number down. I did. You do not have to write this number down, but I wrote it down just for the video. So you've got negative 4.01802. 3005. Now how do you get rid of ln? Well, to get rid of the natural log, you hit second ln in the calculator, and what that makes is this little e key. So it raises it to that power. So you're going to basically e raise to that power, second ln, copy and paste that number down into there, and you will find the x. And once we get to x, we are now going to round to sig digs, and you would be getting 0.0180 molar. And it is hydrogen peroxide. Okay, not too bad, just algebra. Okay, we'll move on to the number 2. Number 2, it says sugar sucrose decomposes in an acid solution to the simplest sugars glucose and fructose. The rate expression is initial is K sucrose. Notice it raised to 1 power where the rate constant is, and notice our rate constant is also giving it away. So this again is first order. If the original concentration of sucrose is 0.01, so where we're going to put that, that is going to go here. What is the concentration after 5 hours? So we're looking after 5 hours. And then we know the K to be okay, so we're going to take a second to work that one. You'll notice that that one's going to work the exact same way. So I'm going to go ahead and just start plugging that in, and then maybe you could plug in as well. ln of the remaining amount minus ln of the original amount equals, remember the negative K and then our time was 5 hours. Okay, so rather than go through all the algebra, again, do this side, add that over. You take a second, see if you can get this. Pause the video, see if you get the answer. Don't forget the ln when you bring it over here. Okay. The answer you should be getting for x is 0.0035 molar. And it was sucrose, so you can write sucrose. Okay, I'm going to go ahead and write this number up here in case you're wanting to check your number. And there we go. So that should be easy. So that was just what we just did. So I wanted to come down here and show you this one. It says, we'll find the half-life of that. Well, this makes a nice little triangle, 0.693. This is first order, so make sure you only use this one for first order. But the way the constant and half-life are related, it's always 0.693 divided by the other. So to find the half-life, which we call T1 half, you simply go 0.693 divided by 0.208, hour to the -1. And because that -1 is on bottom, it flips it to the top, and you actually get a whole number. And we've got 2 sig digs, or I just made that up, I don't know, where I got 2 sig digs. Oh, 2 sig digs coming from right there. I was like, where did I get 2 sig digs? You get 3.3 hours. I think you might get 3.33 if you do 3 significant digits. All right, the last example on here, I wanted to show how you deal with the percents. It says calculate the time required for 87.5% of initial concentration of sucrose to disappear. So this is the same equation, so it has the same 0.208 hour, so it still has that. And so we're looking for time this time, so I don't know that. I could put this in if I wanted, 3.3 hours. So 87.5%. Now I could take 87% of that original amount and work with that original amount, but here's going to be my suggestion. Anytime you're dealing with percentages, you could always let the original amount be 100, and then the remaining amount be how much percentage is remaining. This says calculate the time required for 87.5% of the initial concentration to disappear. So if 87.5% is disappearing, is that how much is remaining? No, it is 100 minus that that's remaining. So I could let, and really, believe it or not, with amounts, you could work with percent. If it bothers you having percent in there, you could actually call it grams. It doesn't matter. And then this is going to be 12.5. Let's just go ahead and put percent. I just want to show you that percent works. Works just fine. Still first order, so the natural log of the remaining is always first, 12.5 minus natural log of 100 equals negative, don't forget the negative, k, 0.208 hours to the -1 times the time. That's what I don't know, so I don't know t. There's my x right there. If you prefer x, you can do x. So you can do this math. Instead, now how am I going to get this over? A lot of students go, now add that over. No, this is actually being multiplied. So you're going to need to divide both sides by a negative 0.208. Divide both sides. I left my little percent signs off of that. Now, it is important on the calculators that, because when you do this, it opens up a parentheses, you close it, opens up a parentheses, and close it. Some calculators need you to go ahead and do this in the calculator, hit enter, and then hit divide by negative 0.208. Some calculators will not handle it very well if you try to do that all in one step. So be careful with that. So you should get a time of 10 hours. 9.99999 something, but we've got 2 sig digs going on. So it takes 10 hours for this to decompose to that percentage. How could you make sure you did it right? You can, of course, plug it back in. All right, example number 3. The gas phase of decomposition of, well, that's basically hydrogen iodide because it's a gas, is making half a hydrogen molecule and half a I2 molecule. Has a rate constant of, now notice, this is where I wanted to show you. What's the unit? That's a rate constant. That's my K. Do you notice here with the unit? This is second order. That unit is giving it away. So we've got to use the second order equations when we get ready to do this. You're going to see temperatures in here. We're not ever using the temperatures, but rates are temperature dependent, but we are working on concentration right now, so we're not going to worry about the temperature. How long must we wait for the concentration of HI to fall from 0.01 molar to 0.005 molar? So, first thing we want, we've got the K. Let me put him up there. 30.0 molarity to the -1, minute to the -1. and we're looking for time. We don't need to worry about that half-life. Okay, so our formula here is 1 over the remaining, which is 0.005 molar, minus 1 over 0.01 molar. This one doesn't have a negative in front of the K, so that's kind of important as well. And it is 30 molarity to the negative 1, minutes to the negative 1. And our X is here, our time. So we're going to do the math here and then divide both sides by 30. You should get a time of 3.3. Let's figure out what the units. You see your units on your K. These molarities are going to cancel out, and it's going to leave you with minutes. And I guess this would be, I see 3 sig digs, 2 sig digs, so we'll go with 2 sig digs again. All right, part B. B says calculate the concentration of HI after 10 minutes. So 10 minutes has gone by. So our original concentration apparently is still this. We're looking for that remaining amount. I wanted to do this one because you're going to see X is going to end up on bottom. So it's just algebra. That's all this is just algebra. 30 molar negative 1, minute to the negative 1. And minutes is good. So 10 minutes. So we're going to have 1 over, we don't know this guy this time, minus 1 over the original amount, 0.01. There's no negative for the second order, so it's just 30, molarity negative 1, minutes negative 1, and then our time is 10 minutes. Okay, so we're just going to multiply those. We would end up adding this guy to the other side. So notice where your X is. You've got 1 over AR now equals whatever this equals in the calculator. And I did not write that down. Anyway, I did not write that down. So that's going to go there. So you can do that. But notice your X is on bottom. We've dealt with this before. So you need to either take the reciprocal or you need to put this answer, whatever this answer is coming out to be. I do apologize for the video second class, of course, we're working in. Whatever this answer is, you could put it over 1, and then you could cross multiply. I do have the final answer. I just don't have. So you would get 0.0025. Oh, I guess that's what that's probably equaling then. Okay. Not bad. Last one. Number 4. The rate constant for the transformation of cyclopropane to propene, we'll learn what that is at the end of the year, is 5.4 times 10 to the negative second. That's just to the negative second, hours to the negative 1. So for what order is this telling me? What order? This is first order. I haven't done any zero orders, but the zero orders are the most simple. So I didn't really worry about the zero order. So first thing it says, what is the half-life? Well, it's first order, so to find the half-life, it's T1/2 equals 0.693 divided by my rate constant, which is 5.4 times 10 to the negative second hours to the negative 1. And we are going to find the answer to this to be 120. I think it's 12.8 hours. 12.8 hours. So it's either 128 hours or 12.8 hours. I can't see if I wrote that dot or not. So I think it's 12.8 hours would make sense. Okay. What percentage of cyclohexane will be consumed after 51.2 hours? So we know this. Okay, we know that. And we know the K. And And what percentage? Well, anytime you're dealing with percents, you could deal with 100 as your original percent, and you can find the other percent. So we would have the ln of I don't know minus the ln of 100 equals, this one has the negative in front, 5.4 times 10 to the negative second hours to the negative 1 times 51.2 hours. So it's not working any different than that first one we did. I just wanted to show you if you're dealing with percentages. So we're going to add the ln of 100 over to both sides, and then the ln of x. And again, to get rid of that x, do you remember that ln? Remember, you've got to go second ln, and we should find that the remaining amount is 6.3%. That's how much remains. Now let's go read the question. The question says, how much will be consumed? If that's how much remains, is that how much is being consumed, gone? No, you would actually have to subtract this one from 100 to find out that 93.7% was consumed, disappeared, reacted, whatever word you want to use. Okay, so that's the half-life problems. I do want to point out something on this one because you are going to have some like this. If you know, let's just make up some numbers here. Just want to make it this. This would be original. If you're looking for the original amount, notice something that's going to happen. I'm going to have to, instead of adding to the other side, I'm going to have to subtract. And unfortunately, I did not bring a calculator in here while I'm recording because I just, on a whim, decided to make this up. Okay, notice I would do the same thing. Do you notice this here? So I'm going to multiply, and then I'm going to, instead of add, I'm going to subtract. This is going to work the same way as we just did, but there's one catch, and I do show you this in class. The catch is the fact that this negative is there. So in order, before you go second ln, you have to get rid of that negative. So you have to divide both sides by -1 in the calculator if you want to think of that. My algebra teacher said just change the sign. So you have to do that first before you go second ln and make that e. So anytime you're trying to solve for that original amount, that little negative hanging out front is going to be a little bit of a problem. You're going to see that same thing happen with second order because of that negative hanging out in front. So you got to get that negative taken care of. So I hope this video helps. Please come in and see me if you need additional help. Okay?